Now you're live.
All right, does it? No, maybe?
No, I said
I think you gave me the wrong link.
What? It was the wrong link. Oh,
I
you.
think you gave me the old link. Now inserted it wrong. Good, or you need to change user change to this somewhere. Everything going on.
Let's hear. Should I do like my videos?
Channel.
Oh my goodness. Whatever that is, it looks wonderful. Oh, shit.
Is that you?
No.
Yes.
This is
how long ago was that?
It looks like the newest one.
2012. It's only 3 years old.
The newest one is not a thing.
I mean, you're still broadcasting the one you are. I think you just gave the people in here the wrong one.
Yeah, there it is. By now.
Yeah, give them that link.
Oh. Oh my goodness. Oh, whatever that is, it looks wonderful. Oh. All right, so that's real embarrassing.
You really should close it.
It looks like the newest
Because now
one.
I'm capturing video of yourself capturing video.
So it's a little bit behind.
It starts a little bit behind.
Yeah.
All right, well, I guess we can hear me also. So that's good to know.
Yes.
All right, let's get started. So welcome to DevOps Bootcamp. This week we'll be talking about networking. So to give everyone a pretty brief roadmap, we'll be going over something called the OSI model, which lays out kind of from hardware to the user seeing data, how information gets from point A to point B. Then we'll talk about IP addresses, netmasks, how your computer is allocated an IP address, what an IP address even is, and then we'll have a brief activity at the end. So look forward to that. So the first question that you might ask is, what even is a network? So kind of defining what this talk is even really about. And kind of as I briefly mentioned in the little intro, it's essentially getting data from one machine to another machine, although that data can still be sent within the same machine. But essentially, it's getting it from one place to another. More broadly, it's an interconnected network, to use the word in its own definition, of things. And then something that's really closely related to a network is something called a protocol. And a protocol is essentially a method for communicating that is agreed upon by both parties. So you can kind of think of it as the language that computers speak to each other, or how they know what each other is saying. So there's several different protocols that you guys might know about, like HTTP stands for Hypertext Transfer Protocol, is one really common one. So it's basically saying we know how to talk to each other. So now the OSI model that I mentioned, there are 7 layers to the OSI model. These bottom 4 are kind of the primary ones when we talk about networking. So that's how data actually gets from one computer to the other. And then the top 2, kind of 3, are about how your computer handles that data once it actually gets it. So we'll go more in depth into these right now. So the first layer is just the physical layer, and it's pretty much what you expect from a physical layer. It's stuff like Ethernet cables, data buses, how data gets around in your computer, and also the cabling through which data travels. Yeah, pretty much what you would expect. If you look on the side of your computer, you'll notice that there's a lot of different ports, and those are all just different methods of data, places where data can leave or enter your computer. So if you have an Ethernet cable port, an HDMI port maybe, USB, all that good stuff. Does that make sense to everyone? Yeah. We all know what port is. Yeah.
Where is port 80 on the side of my machine?
Uh,
There's different kinds of ports.
Oh, so Ian brings up a good point that a port can have several meanings. One is a hardware port, and another one is
The software port on the networking layer, which we'll go into later.
right.
Just
So
be careful.
yes, so your computer has something like 9,000 ports or maybe more that it can talk to other computers over, but that's not the same thing that we talk about when we talk about physical ports.
I had a question about the OSI. That's not like an actual specification, is it? It's just more of like a high level
I
concept.
actually-
It's a specification. It's the Open
Oh, it is.
Systems Interconnect.
Okay. So it's like actually a protocol.
There's an RFC.
Gotcha.
1190.
So the next layer up is something called a data link. And a data link consists of kind of a couple different things. The one that people may have heard of is something called a MAC, Media Access Control Address. And that is essentially what helps allocate your computer its own IP for servers to talk to. So you might notice, I wonder if I can actually pull it up on here, maybe? Oh, I don't know that I can. Later in the talk, we will show you guys some commands where you can see what IP your computer currently has. And that will give you kind of an idea of how your computer needs to have an address, kind of like a mailing address for servers to talk to. But that's obviously not static because you're always carrying it around. So the idea of a MAC address is something that helps allocate, well, we have all these IP addresses, which one do I give this computer at this moment? And then there's other things like the ARP, which helps layer 2 and layer 3 talk. Yeah. More broadly, the data link layer is essentially two directly connected nodes talking to each other. So you can think of that as being like two computers that are on the same Wi-Fi network talking to each other, two computers that are directly connected by an Ethernet cable talking to each other, stuff like that, where you're not going from one network to another. So that kind of intuitively makes sense to people of how there's different networks and being on the same one is meaningful as opposed to being on different networks. Kind of, a little bit. Might make more sense as we go on. So the next network up is, like I was saying, the idea of having multiple networks, maybe? Okay, so we're still connected on the same network, but now we're able to send variable lengths of data, also known as datagrams. So that's just the idea of packeting the information that you're trying to send and then sending it. And this is where IP addresses actually start to come in. So now we've been allocated our IP address, and within the same network, we can talk to things. The next is the transport layer, and this is where we start to be able to talk to other networks. So now our data can go not just in our own network, but in other people's networks as well, or it can sort of hop from network to network. Essentially, like this is the idea of the internet as we think of it, where someone in San Francisco can send us data on, I don't know, the Google homepage or Yahoo or whatever it may be. So now we start to see a couple of protocols. One of them that you've heard of is TCP/IP. So TCP is the transmission control protocol. And obviously that's something that's used by pretty much every well-known method of sending data that we know. So it's HTTP, HTTPS, SSH, all of that is going to use the transmission control protocol. And then a user datagram protocol. I'm actually not very familiar with what that is.
So the differences between TCP and UDP is that with UDP, you just shoot off the packet and forget it. You don't care if it makes it there or not. It's not super important. TCP has checks built in so that you shoot off a packet You say, I'm sending you 15 packets. Here's a little bit of information about what's in them so that you can figure out if you actually got the same packets I sent. And then the other machine you're talking to says, yeah, I got 14 of those packets. Can you resend the 15th one? It must have gotten lost somewhere. So UDP is really common for things where you don't really care if something gets there or not, like if you're streaming video. If you've lost one packet, you're not going to go back and try to figure out which packet it is and replay the frame that was dropped. You're just going to drop the frame and move on. Whereas something like HTTPS, if you're transferring a really important file, you want to make sure you get every single bit correct.
So handshakes.
Yes, TCP handshakes are a thing. And that's how TCP, it's more complex than UDP. It involves a variety of other things like handshakes.
Sweet. Moving on, the next one is the session. So that essentially controls when two computers are talking to each other. When do they start? When do they stop? How is it managed? What if the connection gets dropped? All that kind of stuff. So the session layer is essentially responsible for beginning, managing, and terminating when two computers are talking. There's a couple different ways that two computers can speak. One is called a full duplex, which is when both can talk simultaneously over the same channel. Another one is called a half duplex, where only one person can talk at a time, but they can both talk to each other, so it's still two-way communication. And the other one is called a simplex, which is basically just one-way communication. Now, that's kind of the root even of the other two. Everything is really just multiple simplexes. But yeah. Next is the presentation layer. So this essentially formats whatever data has just come in to make it so that the application layer, which is the final layer, can actually read it. So it takes whatever jargon it gets in, ECDSI, whatever it may be, and turns it into XML or ASCII, which the application layer can then read and do something with. So this is essentially responsible for organizing all of the data that just kind of came in the form of packets. And then finally, we have the application layer, and the application layer essentially sends the data to wherever it needed to go. So this is kind of like the final destination, and the application knows to either display it to the user or send it to another program on your computer, whatever the case may be. This is what handles that. Are there any questions on the OSI model? No, maybe. Okay. Sweet. So then moving on, I talked earlier about ways that you can see kind of how your computer is interfacing with other computers right now, because hopefully we're all connected to the internet. So one thing you can run is IP_A. If you want to know what that is, I would man it, because I don't know that I can explain it very well. But then ifconfig is going to show you basically how your Ethernet and wireless are configured. So that's where you'll see things like your IP address, your MAC address, whether your Ethernet and wireless are even working, whether they're actually connected to anything. So yeah, you guys can run that and kind of see what comes up. I don't know if we have oh yeah, here's an example output of IP_A. So you can see right here, this is our IPv4 address. So it's 192.168.1.55, and then this /24 is something called a CIDR protocol.
CIDR notation.
CIDR notation. We'll get into that a little bit later, but that is kind of part of how your computer knows where it is and knows how its IP address is allocated. Let's see what else. This is our IPv6 address. You can see that it's formatted pretty differently. Instead of having a number between 0 and 255, we have a 4-digit hex value, and then we have 4 or 5 of those. Yeah. And that is essentially to allow more fluid IP address allocating, and also just so that there are more IP addresses available, more very simplified. What else? Something interesting. ETH2 is Ethernet. WLAN1 is Wi-Fi.
So the ETH2 corresponds to the physical Ethernet port on the side of your computer, and WLAN1 is your wireless card.
Does anyone know? I actually don't know. So does anyone know what the valid LFT forever, preferred LFT forever is? Per chance? The very last line.
Oh, that is related to, it's the lifetime of the lease of the address using DHCP.
Okay. Sweet. All right, Jordan's turn.
Okay, so now we're going to talk a little bit about Netmask and broadcast. Netmask and broadcast are essentially a way of figuring out the block of the network that you're actually on and the other addresses you can talk to. So the idea behind a netmask is that you take all of the possible bits, there's 32 possible bits in an address, and everywhere that you cannot change one of the bits, you put ones, right? So in this case, it's 255, 255, 2550. So we have 8 ones, 8 ones, 8 ones, and 8 zeros. That means that there are 256 numbers we can use in the last entry here to the 8. So there's 8 bits we have to play with, right? So if we take a look at an address here, that's not a good example I was expecting there, because this is confusing. Let me see, there might be a better example on the next one. Oh, that's the Netmask. Excuse me. Wait. Okay, we'll go here. So in this case, we have 2 255s, and then we have a 192 here. So we have 8 zeros plus 6 more zeros, which tells us that everything starting from everything in the last octet is part of the network, plus from the address we're on, we have 6 more bits to play with, which is, I believe, 64 more addresses. So that tells us that from 192.168 up here, then 90, it's 65 through 128, plus 0 through 255 for every one of those numbers 1 octet by. Does that make sense at all? It's a bit strange, but that just tells you it tells you all the other addresses that are on the network you're on. So here's a slightly more fleshed out example, which is the one I was hoping was in the slide somewhere. Here we have the same netmask where we have 6 bits and 8 bits, right? And then we have this address. The starting network is .64.0. That's the first address in the block. And if we have, here's the example of all the available hosts that I was just saying. There's 64 through 127 and 1 through 254 because 0 and 255 are special. The reason that 0 and 255 are special is due to the way that Ethernet and IPv4 works, which is more or less that every address just yells really loudly and every other address listens. So you have what's called broadcast address, which is a specified address at the end of the block, the last octet of each one, and 255 is the last one. So 127, 255, and that is the address to which everything broadcast when it's trying to find another address to talk to. So if you are 192.168.64.10 and you want to talk to someone who's 192.168.64.11, you know that address, we don't actually know which machine it corresponds to on the network at a lower level. Because remember, IPv4 address is layer 3, and you actually need layer 2 to figure out which physical machine to talk to. So you yell on the broadcast address, I'm looking for .11, and .11 responds,
this is me, here's my MAC address. And then you can talk to them. And that's actually part of what ARP does. If we look back in layer 2, ARP is actually kind of special because it's technically between layers 2 and 3. ARP is the address resolution protocol, and you can think of it as a table of MAC addresses and IP addresses. So it maps a MAC address to an IP address. MAC addresses are layer 2, IP addresses are layer 3. So it kind of falls between the two layers. So that's what netmasks and broadcasts are used for, along with routes. Routes are special too. You want to talk about routes?
Sure. So routes are kind of like, you might think of them as like, how do I get to my house in Kelly? It's essentially like the route that your data is going to take from one computer to another. So we have, here you can see kind of the destination. That's, as you might imagine, where we're trying to get to. And here we can see an IP address. And then I'm not sure what the -n is.
The -n gives you the actual routing table instead of giving it to you, and it gives you the numerics instead of trying to.
Okay, so instead of like
resolve an
foo.osUSL, it'll have
exactly
the actual
Yep.
numeric.
So, here, if you want. So for this first one, I really should have a pointer. 192.168.1.0, and we have a mask of 255.255.255.0. That means there are 256 addresses in this block. And what that is telling us is that if we want to talk to anything in those 256 addresses, we talk to this particular gateway, in which case star is actually representing our default gateway. So all the traffic ends up going through it. The reason that 192.168.1 and link local are in there, even though they're pointing to the same gateway as the default, is because there are sets of reserved address spaces that are used for, they're set aside for certain specific uses. So they're also routed slightly differently, even if you usually end up routing them to the same place you route everything else. So if we do -n, which is numeric, we have 0000 with a mask of 0000. That means all the bits are there. So that means anywhere we want to send any traffic, it goes through here. And our gateway in this case is 192.168.1.1, which that means that the IP address, our wireless, is usually wireless network, is on is 192.168.1. something, probably. And we're going through 1.1. Traditionally, the router is the first address in the block. So in this case, it's probably /24, which is 256 addresses, so you have the last octet to play with. Yep, that's that. So this slide was put in kind of to motivate a few things to think about. I don't really want to talk to them too much, but it's worth thinking about, which is when you actually go to start a network connection, you have to consider how the network connection itself gets bootstrapped, which is, for example, if you say have a device that can do full duplex negotiation, and I have a device that can only do simplex, how do we negotiate that? If you just assume I'm going to start talking on a duplex channel, and I assume I'm going to start talking on a simplex channel, that can get really confusing, right? There are ways to solve that. And obviously it is solved because you can have a network connection. But it's a really good thing to think about, and it's a really good thing to look up if you're interested in exactly how that works. It's a little bit more complex than I want to get into right now, though. Another thing that's worth thinking about is if you have a static configuration of your IP addresses, or if you have a dynamic configuration of them. For example, with servers, it's really common to have static because they don't change ever, usually. Whereas for your laptops, they're almost always dynamic because as soon as you go to a different network, you need an entirely different router and different gateway. You're going to get a different address. For example, the OSC network uses an address that starts with 10. 10.0.0.0. Those last 3 octets are all available for reserved space for local addresses. Your home router probably uses something that starts with 192.168. So your laptop has to be able to handle all these different configurations. The way you solve that is called DHCP. We can talk about it a little bit later. So CIDR, which Lucy mentioned earlier, is classless inter-domain routing, which is a really fancy way of saying I don't like netmasks and broadcasts. Can we put it into an easier form? The answer is yes. Yes, you can. So if we look back at that IPA example, IP-A, or no, just IPA. Yeah. Here we have this /24, right? But we also have our broadcasts, and our netmask is implied because if you know your broadcast, then you know your netmask and you can calculate it. But the idea is that we should have an even easier notation, which is this magical /24 that tells us all the information we need to know. So what we end up with is you have the slash and then a number. And do we have a, maybe I'll use it. So you have a slash and that number. The number of bits, the number of addresses that are in your block is 2 to the 32nd minus the number after the slash. So if we had 10.0.0.0/8 as our network, we would take 2 and 32 minus 8, which is 2 to the 24th, which is what, 256 cubed. I don't know what that is off the top of my head. It's a lot of addresses. So one way you can think about that is that, and actually since you have 2 to the 24, you have 2 to the 24 addresses, you still need a netmask and you still need a broadcast, right? CIDR contains a couple of rules for how you actually calculate those. The simplest way is that if you know the start of your block, which in this case is 10.0.0.0, then we know that the netmask is 255.0.0.0.0. And we know that our broadcast is 10.255.255.255, the last one in the block. One thing that's important to note is that the block is, the slash represents that you're in a particular block, and that block is position independent. So if we have 10.0.1.0/8, that would actually still be in the same block. And the way you calculate those boundaries and how they fall is contained in some rules in the specification that defines CIDR. It's a little bit complex. Luckily, we have this thing called IPCalc that will generate that for us. So if you had 10.0.1.0/8 and you didn't know where the start of the boundary fell, but you knew you had the /8 block, you could do IPCalc 10.0.1.0/8 and it will tell you where in the block everything falls. Which I wish we had a slide on, but we didn't. Okay, I can show you guys an example at the end. So, static configuration.
Yeah. So now, like Jordan mentioned earlier, static configuration is used for static computers, things like servers. They're not going to move or change very often, as opposed to dynamic IP addresses, like you talked about when your computer is moving around a lot and changing from network to network. It needs to be able to handle that. Static IP addressing is not going to do that, but so for a static address, I guess, it obviously has its own IP address that it knows in advance that stays the same pretty much forever. It has its own netmask. It has a default gateway, and that's how other computers know to talk to it, kind of like we saw earlier in the
routing table.
Yeah, in the routing table. So that gateway. I wonder, can I do this? Yeah, right there. That's also static. That's something that the computer itself knows and can tell other computers. And then a DNS service or server.
Which is, if you actually, does anyone know what DNS is? A little bit?
Domain name service.
Domain name service, exactly. So DNS is how you translate something like google.com into an IPv4 or IPv6 address. So your computer actually knows how to talk to it. So DNS service is really important it's important to have a DNS server because if you actually want to refer to things by nice names that you can remember, like google.com instead of google.com's IP address, you need DNS. So most static configurations, you'll have a DNS server in advance that you run or someone else you know runs that you use. There are ways to dynamically allocate DNS servers even with a static configuration, but it's harder.
How do you like run your own DNS server, and how does that like?
It's a great question. We have a talk on. Do we have a talk on DNS scheduled?
I think next week is DNS.
Okay, I will talk about it next week.
Okay, cool.
It's a really cool answer, but it's complex.
Yeah.
But we'll talk
Sounds
about it.
interesting, like how it like propagates and
Yeah,
stuff, but I
it
don't
is.
know how it works.
I'm not going to talk about it because otherwise I will. I've given talks about DNS before at conferences. It's really fun. I like it.
I will put like some channels to that even.
Yeah.
Where you, someone can.
But one thing I wanted to ask to see if anyone is really paying attention: why do you not have to know in advance what your broadcast address is?
It's the last one.
Yeah, exactly. You can calculate it given your IP address and the DNS.
So essentially the idea with this is like you need to know pretty much everything about your own IP configuration in order to be static. And it's all constant essentially. So then as opposed to that, we have something called dynamic configuration or DHCP, which is dynamic host configuration protocol. Control protocol. And that is essentially the protocol by which your
configuration protocol. I'm sorry.
Oh.
You were right.
I was guessing, but so that's essentially like you can think of your computer as a host in the dynamic host configuration protocol, and it's essentially how your computer gets an IP address when it is on a network and how servers know how to talk to it. Question, I'll pose it to you guys. How do you communicate over a network without a specific network configuration? Who has any ideas?
I kind of touched on this earlier, just a tiny bit. Has to do with broadcast.
Do you ping the network and ask it to broadcast the settings or something? No, okay.
Yes, kind of. You're on the right track. But here's an interesting question. If you don't have a network and you have no information about the network that you're going to be put on, how do you know the broadcast address?
You kind of just said it in, right? You just don't even answer that. Yeah.
Request for the broadcast address.
There's actually a reserved set of global broadcast addresses that everyone listens to. So I can show you guys that later. There's a really cool Wikipedia page on all the reserved IPv4 space and what they're used for. So like there are some addresses that are reserved explicitly for documentation purposes. If you need an example address for some documentation you're writing, you use one out of that block. But there's also an IP address reserved for broadcast when you have no idea what network you're on.
Yeah, so essentially your computer asks for its own IP address, and whatever network it's on usually has hopefully a number of IP addresses, although that's beginning to become a problem with IPv4, which is why we're actually starting to see a lot more IPv6 usage. But yeah, it essentially asks for that configuration, and then whatever network it's on gives it to that and then routes all the communication to it. So he was talking about how there's a couple of really special IP addresses. You guys have probably seen 127.0.0.1. That's your own machine, essentially. And then I added the CIDRs. They're probably somewhat accurate, but you probably aren't going to see, like, if you type in 127.0.0.1, it's not going to fill in with the rest of the CIDR. 192.168, like Jordan mentioned, is usually your home router. I don't know, is that just a Comcast thing, or?
No, so 192.168.0.0/8 is reserved for local area networks. So anytime you have a network that's behind a firewall and none of those addresses are explicitly available, none of the computers behind that network you want to be explicitly available to the wide internet on their own. You do something like that. Same with the 10.0.0.0/8 and the 172.16 Those are all reserved specifically for that use case of local area networks. The 169.254 is reserved for the special case of when DHCP fails. If you've ever seen DHCP fail and you get some really weird address, it's like 169.254.1.1 or .0.1. That's because your computer has no idea what it is, so pick something in that block.
Bad sign usually.
Yeah. Almost 99% of the time, you're going to end up on a network that's not routable, and your router's not going to be listening on that network. It's just a defined way of failing, so that you can fail gracefully.
And then I'm not actually sure what the idea of private versus public.
It's just the idea of local versus wide area networks.
Okay, so like talking to computers on your own network versus a different
Versus
network?
behind firewall.
Okay.
Yeah.
So I guess maybe the best example of this is like we have a little Raspberry Pi at my house that we used to serve stuff like movies and music. So that is a private IP address where only people in our house area can access it on the local area network.
I can't ping it from right here. I
Right.
can't talk to it.
Yeah, it is not a worldwide web server. It's just something where when we're on the network, it has a static IP that we can access it on. And so I guess that's kind of the same idea here, is the idea of a private or local access network versus a more widely available network. Like OSU's network is obviously a public network that pretty much anyone can get onto.
So some of these slides were from last year. I know the guy who gave this talk. These are 3 items that have the same name as a type of network device. Does anyone know what the first picture is?
Looks like
It's a router.
standard.
Call it.
Which is also a networking device. Then you have a switch, and finally you have a hub. There are 3 types of network devices. So how it ends up working is a router is responsible for translating and possibly changing traffic as it goes through. So for example, you have a router at home that is responsible for tagging all the traffic that goes through it so that it knows which computer to send it back to when the traffic comes back, because you only have one IP address most likely at home. But you have multiple devices behind your router. So the way that works is you have your local area network, which your router assigns IP addresses to everything. And then when it sees traffic come through from your laptop, it tags it and says, hey, this is laptop traffic. And when it sees return response to that traffic, it knows to send it back to your laptop instead of to your phone, for example. A switch and a hub are very similar concepts. The exact details of how they work is more about how they're internally connected. But you can think of both of them as objects which take a lot of connections together, but don't actually control anything with the connections. So your router has a local network over which you have your devices connected and they get the IP address from the router. And the router does a lot of work behind the scenes to make all of this work. A switch and a hub don't do any of that. The difference is that switches and hubs work on different layers of the OSI model. But in general, for kind of our purposes, they're pretty similar. So if you have a bunch of statically configured machines at home, you can connect them all through a switch and they'll talk to each other just fine. If you try and use a switch and use DHCP and you don't have a router that's managing the DHCP, it's running the DHCP server, then it's not going to work. That's kind of a short way of explaining this. We can talk more about them if you're interested too.
More network devices. You guys have probably seen an actual router.
These are the pictures. That's an actual router. That's mostly what a switch looks like. It's a small switch. And I'm guessing on the next page is a picture of a hub. No, switches and hubs generally look the same from the outside. Yeah.
I hear that switches are faster than hubs because of the way they are working. They send all the information to all ports.
Yes.
And but switches, they address each information to
Yep. And it's the same thing with routers. Switches and hubs both beat routers because they don't have to actually set the traffic and do anything with it. They just relay the traffic. But yeah, in switches, everything is connected to everything. In hubs, they're not everything is connected to everything, which makes things a little bit faster in switches. It also means you spam a ton of traffic over everything, and switches can end up being complex, especially when you start plugging switches into switches. You can run into some things called broadcast and multicast storms that will take that entire network if you're not careful. Those are fun.
I'm not sure what the really was like.
It's a more in-depth talk of switches versus hubs. I don't really think we need to go into it.
I believe this is the last slide.
Is it? Perfect. Cool. No, this is the last one. So the guy who gave this talk previously also gave a talk on collisions.
Ethernet, when it became a thing, was really exciting to some people because it was really simple. It was a lot simpler than the protocols that existed before it. But it also introduced a lot more complexity because it didn't account for things. There was a type of networking before Ethernet called token ring. And the idea behind token ring is you have a talking stick. Whoever holds the talking stick gets to talk on the network, which is awesome because then you know exactly who's supposed to be talking, you know who it is, and everyone who's listening listens. And you don't have to worry about things like you have two packets come in and two different connections at the same time, and which one goes first, and do you have collisions, and what if you start sending all packets? What if you send trains at 80 packets down the switch at the same time? And electrical signals get confused. What happens? Turns out packet collision happens in Ethernet. Ethernet decided we don't care. Solve it on some other problem. It's someone else's problem. It's not the actual hardware's problem. It's a higher up level. That's where TCP is really important, is because it's really, really easy to lose packets. It happens quite often. In fact, you can have, we say, I'd estimate you can have 5 to 10% packet loss and not even notice. You might notice if you're doing something that's really packet sensitive, but most likely you won't even notice. You have to get to around 70 to 60% packet. Well, you have to get to 20 to 30% packet loss to really start noticing. But one of the really crazy problems it introduces is now Ethernet allows packets to collide, doesn't care. It leads to a lot of really complex situations where once you start pushing so much traffic over your Ethernet devices, everything starts colliding, and you run into problems where nothing gets through. And instead of having a nice linear congestion where you send, you have like 10% of your capacity is utilized, and maybe you have 10% collisions of all the packets that go through, and 90% goes to, it gets really nasty. Instead of being all nice and you can trace your packet loss as you increase your bandwidth, it's much more crazy. You basically have no packet loss and then you have tons. So there's also much more complicated situations like wireless networks, and how do you manage who's talking on a wireless? Do you have a question?
Yeah, where does the packet get resent if it's lost, like somewhere in between like the server to like a wireless network?
Yeah, so what happens is, of course, you're on TCP. You're not using UDP at that point. The machine that is supposed to be receiving the packets says, hey, I never got packet number 15 out of 30. And then it asks for that packet back. The other server says, okay, I'm sending you one packet out of one packet, and it was packet 15 in this other chunk I sent you before. Here's the new information about it to calculate and make sure you got it at the same time. And then when the machine receives a packet, it says, hey, I received packet number 1, I received packet 2, I received packet 3, I received packet 4, and goes through. That way the original machine that sends it knows that everything made it there.
Okay.
So essentially, you can think about it, it's kind of like receipts at a store.
Mm-hmm.
You buy something in a store, which is equivalent to sending a packet, and the store gives you a receipt, and they keep a receipt for themselves. So you know that the sender knows they sent it, obviously. The machine that gets it sends back a receipt to the sender, so the sender knows that it was received correctly.
Okay.
And you can also run into more complicated places where, for example, the receipt can, you can run into situations where you can send packets, but you can't receive packets from someone. And you can run into situations where the other machine will try and send you back packets and they'll never get there. And so TCP has ways of dealing with that. Obviously, if that keeps going, you can never actually have a successful connection. But if you lose packets going, if you lose receipt packets, there are still ways of managing that. The kind of canonical example is the handshake for TCP, which is how you start a TCP connection. It has what's called synchronize, which is like, hey, I want to talk. Then you have synchronized ACK, which is synchronized acknowledgement. That's the second server, the one that the server that's initiating the connection sends the synchronize. The receiver sends the synchronized acknowledgement. And then the original server, again, sends an acknowledgement. That's your traditional three-way TCP handshake, is ACK, ACK. But yeah, collisions, they're a thing. They happen. They get much more complicated when you start going with more complicated networking. Once you start talking about things like wireless, like CDMA or 802.11, you really get into some interesting ways of avoiding collision and detecting when collisions occur and how to correct them. There's a really interesting article here that's linked. It's worth reading, but I don't really want to talk about it now.
So now we're going to move on to our activity. So if you guys go to the Bootcamp exercise website, GitHub, and then can everyone see that URL, or do you want me to write it on the whiteboard?
Why don't you write it on the whiteboard over there? And I will run through the exercise with you guys to start. It's pretty simple. Yeah. Where is that hiding?